Here in exercise 16.11, I would like to play around with these Fourier integral formulas and Fourier transform, and then also the sine and the cosine version of these. And we do all this with one given very simple function, and the function is here. So let me plot this. F of x is 0 for x less than 0, and it is 1 between 0 and 1, and it is 2 between 1 and 2, and then it jumps down to 0 again. So this is our function f of x. And we know already if we do the Fourier sine integrals or the Fourier transforms, we get half the value at the jump. So we can fill already in the jump points here, which the Fourier integral formulas will attain on the jumps. Okay, so now the problem is A, find the Fourier integral formula for f. B, find the Fourier sine integral formula for f. C, find the Fourier cosine integral formula for f. D, find the Fourier transform. E, finds the sine transform. F, finds sorry, I fell asleep a little bit. Okay, to make this more interesting, I give myself 100 points for each of these exercises. All right then. Let's start with the Fourier integral representation of this function. And I just basically go back to the book wherever we studied this and grab me all the formula that I need. So for the Fourier integral formula, and now here I write it as f of x plus f of x minus divided by 2, because if there's a jump, right, then we go to half value. Good. So then this can be written as an integral from 0 to infinity, a coefficient a omega times cosine, and then another coefficient b of omega times sine omega x d omega. And these coefficients, they're given right here. So here is this a. And a would be taking the original function and integrating it with the cosine omega x from minus to plus infinity, coefficient 1 over pi. And the b function is right here. It would be integrating f with the sine. Okay, so if you have these formula there, then what you have to do should be very, very straightforward. You plug in f, you integrate sine and cos, and then you get your coefficients. So let's do that here. So here is my a. Very same formula, I write it down again. However, I used already that left of 0, the function is 0, and right of 2, the function is 0. So the integral really is an integral from 0 to 2. And then we can split it even up. So between 0 and 1, the function is 1 times cosine. And between 1 and 2, the function is 2 times cosine. Okay, but this is all not difficult at all. We integrate cosine, which is sine omega x divided by omega. We still have the factor 1 over pi from the front. And then we evaluate the first one between 0 and 1, and the second one between 1 and 2. And you sub in the numbers, and then this is what you get. And then I use one of these double angle formulas. So this is 1 over pi minus sine omega divided by omega plus 2 times over omega, and then a double angle formula there, which is 2 sine omega cos omega. And then I can factor out a sine omega divided by omega. So I get sine omega divided by pi omega, and then we have a minus 1 there. And then we get a 4 cosine omega right there. Let's move on to the b coefficient. So in the b coefficient, we can again change the integral from 0 to 2, because this is where the action happens, and then split it up into an integral from 0 to 1 and from 1 to 2, where we then have integrate sine of omega x. So we integrated sine many times, and then this is what we get here. And again, we can use a double angle formula. Then this becomes 1 over pi omega, 1 plus cos omega minus 2. And then we have 2 cos square of omega minus 1. Okay, and then if you simplify this a little bit, then we get 1 over pi omega, 3 plus cos omega minus 4 cos square omega. But I mean, this formula is then again here. So then we take the a of omega and the b of omega and we sub it into the Fourier integral formula here and here. This is an a, of course. You can write the function as an integral which involves all these sine and cosine terms. Cha-ching! We get our first 100 points. Now here's an interesting fact if we use the complex Fourier integral representation. And I recommend that you get familiar with this too, so that instead of sine and cosine we have e to the minus I omega x as an integrand. Then the coefficient is called f of omega with a big F, which is again 1 over 2 pi integral from minus to plus infinity integral f of xi e to the I omega xi dxi. We can integrate this the same way as before, so the integral boundaries change from 0 to 1 and from 1 to 2. In the first interval the function is 1, in the second interval the function is 2. And so here we have to only to integrate exponentials. And then if you perform this integration, you get this term here. And now we have only one coefficient, which we sub into the Fourier integral formula in the complex version, and then we get this. Okay, so this was not a question I asked earlier, but we did it so nicely, so I give me another 50 points. Cha-ching! The Fourier sine formula is given here. You remember, for the sine, we use the odd extension. So we take the function, which is defined from 0 to 2, and we do the odd extension, which defines it also from minus 2 to 0. And then we could find the sine integral representation with the coefficient b of omega by integrating the function f with the sine from 0 to infinity, and we did get the additional 2 here on top. Alright, so let's integrate once more. So here it is. Instead from infinity we can integrate to 2. We split it up from integral from 0 to 1, integral from 1 to 2, integrate the sine, getting the cosine terms like written here. So then b comes out to be this coefficient. So then we can sub in the b right here. This is b of omega. And then we have the Fourier sine integral formula. Cha-ching! Another 100 points. So the cosine one, we have a coefficient a which multiplies the cosine. A of omega would be f integrated with the cosine. So then f will be split up. It is 1 in the first interval, it's 2 in the second interval. Integrating cosine, we get the sine, and then we get the coefficients a. These are basically the same calculations we did anyways already. We come to the Fourier cosine integral formula for f. Cha-ching! Another 100 points. So we are good. Now let's come to the Fourier transform. Okay, the Fourier transform is basically the same thing, isn't it? So Fourier transform f of omega equals 1 over 2 pi, integral from minus to plus infinity f of xi e to the I omega xi dxi. If we look at the complex Fourier integral coefficient, then we get the same thing. Let's go back. You see here on top, this is where we computed the coefficient of the complex Fourier integral formula. It's the same thing. Which means we don't even need to calculate it again. We can just use the result which we have. And so this is the Fourier transform. The Fourier transform is the coefficient we were looking for. And similar for the sine and cosine. So if we do the Fourier sine transform right here, we integrate f with the sine function, and what we get is the coefficient b of omega we computed earlier. So the coefficient of the sine integral formula is called the sine transform. And of course the coefficient of the cosine integral formula, which is then this guy here, is the cosine transform. Alright, so we have 3 integral formulas, and the coefficients that arise in these integral formulas, they are called the corresponding transform. Fourier transform, sine transform, cosine transform. Oh, I forgot my 100 points. 100 points for sine transform. Cha-ching! 100 points for cosine transform. Cha-ching! That makes a total of 650 points.